Good morning, folks, and today we're going to talk about the electric field for a little bit. So you can see on my screen I have a picture of a field. And so you can imagine if you were walking through this field and you can see how high the plants are, that you would feel them brushing against your legs. So in that same way, we're kind of walking through a field, but a field of gravity. Now let's imagine these plants. If we could have these plants grow higher and higher, and I know they can only grow so high, but just imagine. And don't forget that the earth is curved. So as these plants grow higher and higher, they would start to tilt away from each other just because of the curvature of the earth. Now you don't see it on a small scale like a field like this, but they really are a little bit. And so in the same way, when we take a walk on the earth, we're feeling not the weeds, but we're feeling these field lines from gravity. Now, that's links to the electric field. So the electric field are these invisible lines that extend from a body. And you see that I'm right down there. We talked a little bit about the contact forces, such as friction or a push or a pull. And those are cases where things have to be in contact. But gravity and electromagnetism, they're forces where they don't have to be in contact. If you jump up off a trampoline or anything, you're going to come back down. Gravity will still pull you while you're in the air. And the same is true for these electric field lines. They extend from a body. And I think we saw that picture before we left from the classes. So there's a convention. And we use this little thing called a test charge. And a test charge, the convention is that it's always positive. So we already know from talking about charges that two like charges are going to repel. So the way they do this is when we draw field lines going out from a proton, they always go out, because that's the same direction this positive test charge would be moved, because positive and positive charges would repel each other. So that little positive test charge up here is going to move away. Or a metaphor, a way that I like to think about it is, a positive person gives things and sends good things out into the world from themselves, just like the positive charge, the field lines go out. Now for a negative charge, like an electron, we draw the field lines in, because that's the way that this same positive test charges are always positive, would be attracted. It would be attracted in towards the electron. And to use the metaphor, if a person is negative, they kind of pull everything in. They make everything about them. They only care about getting things for themselves if they're a negative person. We can use these field lines to say, why do the opposite charges attract? So if we look here, from the positive, they go outward, and then they connect to the negative that pulls them inward. So that's the convention, the way we think about it. And you can see that they're showing this with iron filings down here. So these are two wires. So maybe this one here is positive, this one is negative. And the field lines are going out from the positive charge and in towards the negative charge. So everything lines up and it connects, and these opposite charges can attract each other. But like charges, they'll repel because the lines don't connect. In this case, they're both going out. They don't want to meet each other. And so in that case, these two charges would want to move away from each other. And we can kind of see that same thing going on down here in the picture. The problem is, or the little trick is, that there's two ways to mathematically define the electric field. And it's a vector quantity. So some books will put the little line here to show that it's a vector. Not the average line, but they usually put a little arrow. Sometimes they do a full arrow, sometimes they do a half arrow, to indicate that it's a vector quantity. And so the electric field is the force a test charge would feel. The smaller the charge, the larger the force. So think about a small charge maybe being like a golf ball. So if you hit a golf ball with a golf club, you can send it as far as you want, a few hundred yards. I'm not a golfer, but I know they can go a few hundred yards. But if you had a big bowling ball and you hit it with the golf club, assuming it didn't break, that would be like a larger charge. So you couldn't send the golf ball going, or the bowling ball going hundreds of yards, maybe just a few feet at best. So E equals F over Q. And the reason that's handy is because it helps us know the unit that we use. Force is always in newtons, and charge is in coulombs. So for the electric field, it's newtons per coulomb is the unit that we use. There's another way to do the electric field, and that's in terms of the point charge, not the test charge. So that's just some charge sitting around. Let's say it's positive, just for the sake of this example. And it's giving out its electric field. And again, it's still a vector quantity. I guess I should have that bold, or we'll put the little arrow on top of it. So the point charge is the source charge. It's what's causing the electric field. We're going to use KQ over R squared. And just to remind you, because maybe it's been a week or two, K 9 times 10 to the 9th, and I forget the unit right here off the top of my head here, Newton meter squared per Coulomb squared. K is actually not the technical unit. K is a derived unit from this more fundamental constant called the permittivity of space constant. So it's this E sub 0. So K is 1 over 4 pi e to the 0. I think you could see that that's a bit confusing. So we just use K for the most part. There are some equations later on where we may need e to the 0, but we'll get to them another time. So let's do a couple examples here, maybe 2 or 3. So it says, find the electric force on a proton placed in an electric field of 2 times 10 to the 4th newtons per coulomb. So that means the electric field, let's draw it this way. We don't know what's causing it. Maybe it's a wire, maybe it's another point charge. And we have a little test charge, Q. That's going to be a proton. We'll assume that the proton wants to move in that direction because it wants to move away from in the same direction as the arrows. You might say, well, how did I know to use this formula rather than the other one? Because we want the electric force. We're not asking for the electric field or the size of the charge. So we want the force, so we'll just rearrange this. All I did was multiply both sides by Q, just like you're used to doing. And then it's just a matter of substituting. So the electric field was newtons per coulomb. And the charge on a proton, just in case you don't remember, you could always look it up. It's 1.6 times 10 to the minus 19 coulombs. So I think it's pretty easy to see that the coulombs are going to cancel. And we'll easily be left with the force. Now that's a very small force, times 10 to the minus 15. But protons are pretty small. They don't need a lot of force to move them. They're kind of like the golf ball. A little force will move a golf ball pretty far. I mean, I could probably even hit a golf ball and hit it maybe 20, 30 yards, 50 yards maybe. So I don't need a lot of force to move it because the proton's like the golf ball. Now we want the magnitude and direction of an electric field. They're saying it's 30 centimeters. Now this is a negative charge. Q is negative. So just to remind ourselves, the electric field will point in. Just like for the negative person pulls everything in. They want to make everything about themselves or take everything for themselves. And we know a distance. We know we're going to be 30 centimeters, which is, of course, 0.3 meters. In this case, we don't want to use the F over Q value. It doesn't make sense to use it in this situation. We want to use E equals K times Q over R squared. So K is just that 9 times 10 to the 9th Newton meter squared per Coulomb squared. Now we knew the charge. In this case, it wasn't a proton or electron. They just told us what the charge was. Don't forget to square the R down the bottom. It's a common mistake. I've made it myself. And notice also that I made it in meters, not centimeters. And we can calculate the value of the electric charge. So we've had a couple examples, how to use each of the formulas, talked a bit about, well, what is the electric field and what directions do the lines go, and we'll see you at the next video.